Okay, good afternoon and welcome to this afternoon devoted to the seismic assessment strategies for masonry structures. Stadata and Tremuri Project are very proud to present you a panel of distinguished professors and engineers from all over Europe. So I would like to thank them all for having wanted to share today with us their interesting lectures and case studies. I would like also to mention our distributors that have worked this month along side by side with us to let you all be here today. So thank you to Ingwer for Switzerland and Austria, Technosoft, the Netherlands, IDISTI, Slovenia, Croatia, Bosnia and Serbia, Ergocad, Greece and Cyprus, Anashimoes for Portugal. We would like to introduce you briefly to who Stadata is and our activities in terms of software development, and we will do that with a very short video. But before that, the greatest thank you goes to Professor Andrea Penna, University of Pavia, who accepted again this year to be the chairman and key speaker for this event. I hand over to you, Andrea. And again, thank you all for being here. Thank you and enjoy.
Stadata was founded in 1983 by Adriano Castagnone, civil and structural engineer since 1978, and pioneer of scientific software for structural engineering. The company was born to provide civil engineering services and consulting. We have always had a particular interest in the evolving sector of IT, foreseeing the enormous opportunity of applying it in design and computation. Before focusing on software development, Stadata realized important projects both with private and state-owned companies. That's our strength, because beside IT experts, we are professional in structural design. The company is currently composed by 15 employees and several consultants, all highly professional qualified. Thanks to the continuous development of work and collaboration with the university and professional world, it is always able to offer advanced and constant updates to its customers. Application Stadata allows you to face everyday work with simplicity and effectiveness. The company goal does not end with the search of new IT solutions. The offer of Stadata includes support, training and consulting services, including individual projects so that the professionals are immediately operational. Thanks to the technical expertise and the state-of-the-art solution, Stadata is a solution to the real problems of designers.
I think that we can now start the real activity of this afternoon. My name is Andrea Penna. I think that most of you, at least the panelists, know me, as well as I will know all of them. And I take the opportunity to thank all the attendees, all the people that they are joining this seminar. I see now there are now more than 120 participants. This is a very nice opportunity because this is the second international event regarding the Tremuri community, I would say, that the users worldwide and the research professionals involved in the activities of Tremuri. I personally want to thank for their participation Professor Rita Bento of the University of Lisbon, Istituto Superior Tecnico, Professor Naida Ademovic of the University of Sarajevo, Professor Rocco Zarnic does not it doesn't need any presentation. It is well known in the community of heritage structures and masonry structures. He is from the University of Ljubljana. Dr. Anastasios Tsiavos, who is from the ETH of Zurich. Dr. Anna Simoes, who's a researcher and engineer, and she's also active as a reference person for Tremuri in Portugal. Mr. Papadopoulos, Georgios Papadopoulos, who is also a PhD student of the Aristotle University in Thessaloniki, Dr. Jacopo Scacco, Dr. Stigliano Scaglioras, and Mr. Marco Tondelli, that I well know more than the others, as they were working with me in the past. Now Dr. Scaglioras is a researcher at the European Center, Joint Research Center in Ispra, whereas Marco Tondelli is active as a consultant in the field of structural and seismic engineering by the company Stadata. Sismica 360. So our next speaker is actually Naida Ademovic.
Good afternoon. My name is Naida Ademovic, and I'm an associate professor at the University of Sarajevo, Faculty of Civil Engineering. And today I will tell you something about the assessment of masonry structures after 2020 earthquake in Croatia. Before I start with the presentation, I would like to devote this presentation to Dalibor Radonic, who was the owner and the project manager of Project 2, a person who actually gathered all of us together to work on the field of reconstruction and restoration of existing buildings after the earthquakes that hit Croatia in 2020. I do have to say that on behalf of myself and all of my colleagues that we are grateful to Dalibor, and we were proud that he actually chose us to be a part of his team. As you can see in the map, several of the companies are of course from Croatia. There are 2 companies from Italy and 1 company from Bosnia and Herzegovina. This is the composition of our team that worked on the reconstruction and rehabilitation of the buildings that were exposed to earthquake activities in the year of 2020 in Croatia, basically in Zagreb and in Petrinja. How we were actually doing the things, we wanted to do our work according to the latest technologies and of course application of tools. And the idea is that we produce the most, I would say, designs of the highest qualities. And for this, in order to do this, we used 3D scanning software because we wanted to represent the structure as it is on one hand side. And what we are very proud of is that for the modeling, for the structural modeling of the structures, we used 3Modi software, which we find that is one of the best softwares for the assessment of the existing masonry structures. So basically, how we did our work is in the sense that, of course, first of all, we wanted to gather as much as information regarding the structure. So in this sense, the designs from the archive that we were able to gather, we gathered this information. The next step was, of course, the visual inspection of the structure after the earthquake, and in order to determine the level of the damages and, of course, the type of the damages. The next step was the production of the 3D point cloud and the building digital model. And then, of course, it was necessary to determine the structural and non-structural components of the buildings, which was part of the, of course, on-site investigation. During the on-site investigation, we wanted to determine, of course, the mechanical characteristics of the material, because this is one of the most important elements in the process, of course, of the modeling. So what we conducted the flat jack tests and ambient vibration tests in order to determine the eigen frequencies and the eigen modes. Of course, in order to proceed with the recommendations of the Eurocode, first of all, we conducted the verification of the vertical loads, and then we conducted the model analysis. And in order to see, of course, the behavior of the structure, then a pushover analysis was conducted in X and Y direction. The further step was, of course, the check of the local mechanism verification, and on the basis of these calculations, of course, then we decided if there was a need for strengthening methods. Every time we suggested several strengthening procedures, and of course, then we conducted the comparison of these scenarios, these methods, and then we decided actually which strengthening method was the best for each individual, we would say, case study. So the case study that I'm going to show you very briefly is a building which is located in the street Ribnjak 44 in Zagreb. And what is very interesting for this structure is that the structure was constructed in 1903. But as well, it is important to state that from that period, several reconstruction of this building took place. As you can see on this picture here, it is actually this yellow building. What is important to mention is that this building is located in the protection in the area of protection of cultural property of Republika of Croatia, and it is actually in zone A of the city of Zagreb. So the first picture that you see actually the street facade, and on the others on the other picture you see the structure, which is basically from the other side. And what you can actually notice is that there are some reconstructions that took place, and these are these steel, of course, steel columns that you can see on the picture. So first of all, it was necessary to conduct the laser scanning and detail inspection of the site. So from this figure, you see our Dalibor doing the measurements, and of course the preparation for laser scanning that was conducted. The results of the raster scanning is, of course, the building digital model, which you can see in this picture. This was very important because, as I already mentioned, there were several reconstruction and changes to the design of the buildings. So we wanted to exactly have the right geometry of the building in order for our model to be as realistic as the structure is. So the 3D vector digital model of the existing building with the cross sections is presented in this slide. Then, as I already mentioned, it was necessary to gather, of course, all the information from the archives that was available on the left side of the slide. You can see the original design from 1901, and at the bottom in red color, what is actually marked is the walls that were demolished, and on the right hand side you have actually the new walls and the new parts of the structure were constructed. What was as well necessary is, of course, to determine the material from which the structure was constructed. As we all know, masonry constructions can be constructed of various masonry elements, and in this specific case, these were solid, we would say solid bricks for this area. And what is as well very important is the time of construction of the buildings, because at that time we can connect this, of course, with the valid construction technical regulations, and basically we know what kind of design was done at that time. And during the in situ investigation, it was as well necessary to determine the position and, of course, the distance between the timber beams that were located on that were actually creating a slab of this structure. The next step was a very detailed visual inspection and determination of the damage. This was done in a very high detail, and what we wanted to see is, of course, the direction of the cracks, so the pattern of the cracks, the width of the cracks, because this was very necessary in order that when we actually do the modeling of the structure, we wanted to compare, are we actually through the modeling procedure, are we actually going to have similar damage as the building actually experienced this damage after the earthquake that hit Zagreb in the year of 2020. So on this slide, you can as well see this is the level of the first floor. You can see, of course, the description of the damages, and on the right hand side, you can see the measurement, of course, of the cracks in one of the walls. And what is very interesting is that these were shear walls, and this was actually confirmed in the modeling in 3 Moody, which is presented with the picture on at the right hand side of the slide. Following this, as I already mentioned, a very detailed inspection of all cracks were marked on, of course, all levels, and this was something which is very important in the sense that this structure was constructed in 1903, and the slabs were basically timber slabs made of timber, which means that we are here dealing with flexible kind of slabs. So we would say that it was quite logical that the cracks that actually happen at the connection of the walls and the cracks between the slab and, of course, the structural walls, these is a typical kind of damage for this kind of structure. So we would say this is something which was more than expected. The next step we wanted to determine, of course, for the verification and validation of our model, we wanted to determine the characteristics of the material. So what we conducted a single and double flat jack test, which you can see on this slide, in order to determine, of course, the compressive strength of masonry on one hand side, and on the other hand side, the modulus of elasticity. So basically, what you can see here is that the compressive strength of masonry is 2.2 megapascal, and the modulus of elasticity is only 500 megapascal. So basically we are dealing here with a very low quality, of course, of masonry. In order to determine the eigen frequencies and eigen modes, of course, a dynamic ambient vibration tests were conducted, and based on that, we obtained, of course, the value of our frequencies and the shape modes, which are shown in the following slides. So as you can see, the first eigen frequency was 4.09 hertz, and it was actually bending out of plane bending, and basically this is something that actually happened to the building, which was seen, and in this respect we can state that of course this was something that we had to take into account during our modeling procedure. So of course we chose 3 MORI to conduct the numerical analysis and to actually conduct the seismic vulnerability assessment. So you can see here the model, which was conducted in 3 MORI. So first of all, of course, as I already stated, we conducted the model analysis in order to determine the eigen frequency, and the eigen frequency was very close to the result which we obtained from the on-site investigation. And of course this was we would say the first thing that basically we concluded that our model was done in a correct way. Then of course we conducted the pushover analysis in X and Y direction, and what is important to mention, of course, we took into account the PGA of the actual earthquake that hit Zagreb in the year of 2020. And as you can see, of course, there are some of the elements in the X and Y direction, of course, which are in red, meaning that these analyses were not satisfied. So the idea was, of course, to conduct some kind of strengthening procedure. So once again, here you can see the pushover analysis in X and of course in Y direction, and then of course we decided that some kind of strengthening solution has to be conducted. So first of all, the idea was to strengthen the structure with steel frames and with FRCM on the ground floor and on the first floor, where basically you can see the plans of the ground floor and of course of the first floor, and you can see down the characteristics of the FRCM that we used. And in the middle you can see the steel frames that we actually formed in certain parts of the building in order to strengthen the structure. What is important to state here is that in this situation, what we wanted to do is, because we are here talking about flexible, of course, about flexible slab. So in order, we decided that our first solution was actually to strengthen the slab with the overlapped wooden planks, which you can see on the right, right hand side, and of course you see the position of the steel frames, which were located in certain openings and of course in certain walls. Of course, in the same sense, we conducted the pushover analysis in X and in Y direction. And as you can see, after conducting this kind of strengthening procedure, we satisfied all the calculations had a satisfactory, of course, result. However, then we wanted to try and to see actually what would be the results if we changed a bit the strengthening method. And again, as you can see, we kept the FRCM and the steel frames. However, we have eliminated one of the steel frames from one of the walls. And what was interesting as well in this situation, we said, okay, let us actually change the slab and use the concrete topping, even though we knew that this was not and this is something that should be, in the sense, of course, prevented for the reconstruction of the existing historical buildings, because the best issue would be, of course, to strengthen the structure with the wooden planks and to keep the behavior of the structure exposed to earthquake action as it before. So basically, of course, again, we conducted the analysis, the pushover analysis in X and Y direction. And what you can see, of course, in the lower part is we wanted to compare and actually to see how was the implication of the strengthening method in relation to the original structure. And by comparing these two elements, we have decided that the first solution was actually a better solution, and that was our recommendation for the strengthening of the structure. And we need to state that the strengthening of the structure was conducted for the return period of 19 years. That is for the level of 2 to the creation regulations. And at the moment, there are 2 projects which are being done, and these are the project in Frankopanska Street and Georgicheva. And the model is already conducted in 3 Mori, and we will see what would be the next step. This is all from my side. Thank you very much for your attention.
Professor Rita Bento from the Istituto Superior Tecnico in Lisbon.
Okay, so I'm going to present this case study, the chapel from National Palace of Sintra. And the objective is to present an example of good practice in seismic risk reduction, and it comprises inspection and diagnosis, structural analysis, safety assessment, and of course the proposal of rehabilitation and string interventions. So these are basically the common main steps for the seismic assessment and retrofitting of this kind of structures. So the study starts with inspection and diagnosis, which is the step number 1, through a visual inspection complemented with in situ tests. Then the results were used for construction and calibration of reliable numerical models. So we are now in step number 2, as well as for the definition of rehabilitation actions. Then, after identifying the most vulnerable parts, so we are now in step number 3, some string techniques compatible with the building characteristics and importance are suggested. So, starting with description of my case study. So, it is a chapel. It presents a classic cross-plan shape composed of a nave, a transept, and a choir and a chancel. It was adapted along the years, and the main structural modification was the amplification of this area, the presbytery area. So, we have here the main dimensions of the chapel from the plan side, but I'd like to highlight that the walls, the masonry walls, has about 11 meters high. So we have here some images of the interior of the wall. It contains mural paintings and a very delicate timber ceiling made of hardwood. The roof is of timber elements, and they are supported on about 70 to 90 thick rubble stone masonry, and with some stone works at the corners of the chapel. You can see even that you have here a masonry arch which divides the space between the quarry and the chancel, and it supports the ceiling and of this later space. You can see that there are, from the beginning, there are some in fact, two different. You can see from the image one steel tie roads that were introduced in order to somehow avoid out-of-plane behavior of the walls. So looking now to the type of roof and the timber structures that you have, this figure presents the structural configuration of the two main timber trusses that were supporting the ceiling and the roof of the nave. So this is truss A1, and you can see this type of trusses in the nave and transept, but in the choir and chancel you have the other type of truss A3 with a different configuration, and it is introduced later on. It is not in the chapel from the beginning. So the older trusses, as you can see here, the truss A1, are not self-supporting and thus impose important horizontal out-of-plane forces to the structural walls of the chapel. And in this image, you can see, I think mainly from this image, you can see very well the out-of-plane behavior of the wall. In fact, we found from the laser scanning that the wall from the chapel has a maximum out-of-plane of about 30 centimeters. In terms of inspection of diagnosis, we have performed different types of tests. In fact, we have two teams working in the chapel. IST from my university, so my team from University of Lisbon, and NCREP. NCREP is a private company, and for the chapel, it works together with the conservation and restoration team. So my team have done this type of tests for the geometrical characterization, laser scanning, and we have also the support in the UAV. We have performed ground penetration radar tests, masonry samples collection, flat check tests, and ambient vibration tests. And the inspection, the CREP have been working with the timber structural elements characterization and study of the roof. And the work done included the opening of survey windows from the outside, as you can see here, but also from the inside of the chapel. So the geometrical survey, as I mentioned, of the entire chapel was performed using the equipment, our equipment, and with the laser scanner survey with this what was possible to get a very impressive, very important 3D definition of the geometry of the structure. And as an example, we have here in the right side the accurate geometry that you can obtain with these, and for the definition of the geometric model, it was very important. Just see, for instance, the wall, which is the connection between the chapel and the kitchen. It has a thickness which varies along the width, and this was only possible to get with this type of survey. So with the point cloud dataset, we also developed a Hsb model where we include all the information that we obtain for the chapel, not only from the inspection, but also from the numerical studies. And with this, we can very easily get some horizontal sections and vertical sections that, of course, they will be very useful, mainly in future interventions of the chapel. So very briefly, some types of results that you obtain with our types of tests. So GPR, it was very important in the chapel for characterization of the type of masonry that we have. The sample connection identified by S in this 3D representation allows us to know that we have a significant percentage of voids in our masonry of our chapel. The flat check test identified by F allows us to understand from the inspection window the quality of the mortar, but to estimate some of the characteristics important for characterization of the masonry. And of course, the ambient vibration test were crucial for than for the numerical calibration. For this facade, the sensors, location of the sensor identified with these red circles, and just to represent, we have here the first mode of vibration, transversal mode, as expected of the chapel. This is the type of work that had been developed for the characterization of the timber structure. So it was used non-destructive equipment, as you can see from these images, and it was possible to conclude that the major damage on the timber elements were related to the termite attacks. And the identification of the type and location of these attacks was fundamental for the definition of the final retrofitting of the sail and the roof. So moving now to the seismic performance assessment. It was developed with Tremuri, of course, in which the in-plan and out-plan behavior were studied through the nonlinear analysis. So the chapel is this structure in the middle. It has to be important that it was very important to account for the boundary conditions of this case study. In fact, the calibration of the model based on dynamic characteristics identified with the in situ ambient vibration tests was one of the most difficult tasks that you have to go through for the seismic assessment of the chapel. In particular, because to obtain the correct dynamic characteristics, it was necessary to model the total buildings, adjacent buildings. So we start with some parts of the adjacent buildings, but it was not possible to accomplish the dynamic characterizations that we had obtained in situ. So it was really challenging to get the final numerical modeling. Here we have the pushover curves that have been obtained until the ultimate displacement of the chapel. It is worth noting that in this case, as it was necessary to model the entire Bonnet building. Bonnet building was the building on the left-hand side. You can see here from the plan view. To get the correct dynamic characteristics, you have to model the total side buildings. And as this building is much more vulnerable than the chapel, the ultimate displacement of these pushover curves do not correspond to the typical 20% decay, because whenever the first critical element of the chapel occur, and we can this way consider that you have reached the collapse, the Bonnet building, the other building, was completely already with a significant number of elements that have already collapsed. So for this longitudinal direction, it was very important, the effect of the other buildings. For transversal direction, it was not like this, of course, and you can see that you have for the y direction completely different behavior, with much lower values of the maximum capacity in terms of shear, maximum resistance, and much smaller capacity of the formation of our structure. Just an example of the type of damage that we have obtained in the two main directions. It was basically very clear from here that only some specific vertical elements have collapsed on the chapel, whenever the other have been completely collapsed as well. So after having performing and obtained these pushover curves, the safety assessment of the in-plan behavior of the chapel was carried out following the recommendations of Part 1 and Part 3 of Eurocode 8, and of course the Portuguese National Annex, and we realized that the safety was not satisfied in terms of the global behavior of the chapel. For the out-of-plane behavior, we have considered nonlinear kinematic analysis and performed using according to the macro block modeling approach, and of course we have used, as you can see from these images, a tool in the Tremuri program. Here it is represent all the mechanisms that you have studied, so a total of 8 different mechanisms were studied for this for this case study. So based on these results, some different rehabilitation and string intervention have been proposed for the chapel. So for the ceiling and the roof structures, and you have considered different types of solutions. So try to apply insecticide or fungicide in the timber structures who have been attacked by these termites. We have considered also some new structures disconnect from the existing one in order to improve the behavior of the roof, and it was include some Hsb boards in order to increase the inclined stiffness of these structures, and new connections between the roof structures and masonry walls. Of course, these are rather important also to improve the local behavior of the chapel. For the global behavior, and in order to increase the strength and formation capacity of the walls, we have proposed ground injection with mortar. Of course, it has to be compatible with the original one. And in some of the walls, to apply also reinforced plaster, FRP meshes, of course, only from the outside of the walls due to the very rich interior of the chapel, and these on the most vulnerable walls. For local behavior, despite to improve the connections between the roof and the masonry, some new steel ties were also proposed. So let's start very briefly with the intervention of the roof structure. So considering the current state of conservation and the structural safety assessment, it was possible to conclude that the local strength of the existing elements and the replacement of the damaged ones was too intrusive and extremely difficult to apply on site. So what it was proposed is to have some new trusses identified in orange here in this plan view, along with the existing ones, and this is the configuration of the new trusses that have been proposed for this retrofitting. You can see also that these new trusses, how they are connected with masonry, with this UNP steel profile in order to improve the connection with the masonry walls. So here we have the identification of some of the walls that it was proposed to retrofitting with, and we have these two blue colors. So this blue identify the walls where it is proposed only the ground injection, and the others more dark with ground injection and FRP meshes. And with this, it was possible to fulfill the seismic assessment. But of course, to have some reliable numerical model with this retrofitting masonry walls, it was necessary to somehow understand how these solutions will improve the strength capacity and the formation capacity of the wall. So we have no information about that. So we decided to do some laboratory tests for different types of retrofitting, only with ground injection, and different types of meshes or only meshes, and we managed to obtain the results that then you have used in our numerical modeling. So the results of these laboratory tests, the first one, let's say the preliminary ones, have been already published in this publication, and we hope very soon to have another publication with much more results of this study. So here we have a comparison in this slide, the strength solid lines and non-strength, which are the dashed lines models, which are compared in the transversal direction. So here, Y direction, we have a greater difference when compared to the other direction. So we can see that we have significantly improved the strength capacity, but also the formation capacity for the chapel with this solution, and with this we managed to guarantee the safety of the chapel. In terms of out-of-plane behavior, basically what was proposed is to confirm in situ the proper work of functioning of the existing tie roads, T1 and T2, and to have 2 more tie roads in order to avoid the out-of-plane behavior of some of the masonry walls of the chapel. And basically that's all, just to highlight the importance in these studies, the importance of the first step related to inspection and diagnosis activities, crucial for then the calibration of our numerical models. And these, together with the structural safety assessment, are the only way where you can identify the most vulnerable parts of our structure, and then to propose the rehabilitation and the string intervention. This last paragraph basically is a summary of the type of interventions that I mentioned previously. And that's all. Thank you so much. I hope that this time you have listened until the end.
Yes, sure. And really thank you, Professor Bento, for this really interesting and comprehensive case study. The case study is really a special one. I mean, it is a very unique case study, but also the work you have presented is really comprehensive, and somehow it is really a summary of what we should do every time when we can. I mean, in this case, you have a special case and probably special means as well for this.
So, good afternoon, everybody. I'm really sorry for these technical problems, many software, many systems, and confusion. So today, I'm very happy to be with you. Some of you knows me, some not, but anyway, I am now, how to say, retired research active person. So I'm not teaching anymore, but now I'm doing what I like. And I was also engaged by one company from Zagreb, Planetaris, to help them in assessment of some cultural heritage. What I'm going to present you is some project which is in a relatively early stage. So please do not expect so fantastic data we listened in previous two, but I will more talk about my impression, how with the complex monuments we can have problems, what we can need, how Tremuri can help us. So I'm talking about a monumental building designed by Herman Bolle, known architect, who designed the monumental cemetery in Zagreb. And this building I'm talking about, next slide please, is the building which is actually mortuary, you'll see, but quite sad kind of building, but very interesting as a structural one. So I will give a little bit insight on history of structural alternations, because from its erection 1884-86, it was alternated regarding to some historic needs, and what made the changes in structural properties. Then I will talk a little bit of challenges of Tremuri modeling regarding this rather complex structural characteristics of building. I have a little suggestions for minor Tremuri upgrading, which maybe is already, but I didn't find it. And I have also some suggestions about the 3 new Tremuri structure elements based on my personal research history and my colleagues working on that. Next, please. So everybody knows that Zagreb is very earthquake-prone area. AG for 475 years is 0.26, what is underestimated, everybody agrees. And this area was hit by 2 strong earthquakes in last 140 years. 6.3 ml with epicenter in Zagreb was on 9 November 88. The building we are talking about today is something that was constructed after that earthquake. What we can see in original design, the well-known truth that if buildings were designed or constructed with quite amount of money in that time, they were very well constructed. My own experiences from Ljubljana, Slovenia, is that the best masonry buildings are from the late Austro-Hungarian period or the end of the 19th century, beginning of 20th century, and we can consider this building in the same category. Also, the architect and the builders had very good experiences gained from the recent earthquake, which was just few years before erecting this building. And so the last earthquake in Zagreb, 2020, again affected this building, but no visual damages outside were recorded, neither inside very slight. I'm going to talk about that. Please, next slide. So that is just to get idea, a layout of this building with the cross sections. Well, it's just to get one impression, very monumental one. Please, next slide. And these are these typical internal cracks, which we can say slight to moderate on very expected places. There are some parts of building which were some openings or doors closed. And what is very known is nothing to talk about. And it's on the upper part of the lintels of windows, so nothing dramatic. Next, please. Next, please. Okay. And okay, we have also the digital survey of this building, but very, very good documentation from original building, 1886 documentation, and also design of enlargement in 1913 were available, and also the last 1993, which was very radical strengthening by putting in the reinforced concrete slabs, were available, and very, very good architectural drawings. So we could make a model just based on this data. Next. Next, please. Okay. If just to here you can see in cross section what happened in years. The originally floors of the 1886 and 1913 were single direction timber structures with all these layers as usual. But on 1993, designers of strengthening decide to put reinforced concrete structure above it, just leaving the floors because the investor didn't want to damage the floors because there are some paintings, some decorations. So it's actually new building, new floor system atop the old floor system. So that is something what was the first question in modeling of this building. So until now, I don't really have answer. I just used for the current state the main reinforced concrete structure and the lower one just as a mass attached. Why? Because the direction of the new slabs are in perpendicular direction than the old one. So it would be maybe for Tremuri a future challenge to see how to make a double floor possible, or if somebody knows how to do, I would be very grateful. Next, please. So these are I just made a little bit a model is ready so that you get a little bit impression, and that is the model of the original building 1886. So the next, please. The next. And in after the First World War, they added the part which you see in different color, and that is today's current situation with reinforced concrete slabs and beams. But also we are going to make intermediate system analysis where the configuration of walls is here, but with only wooden floors. So we'll have actually 3 models, plus one from 1934, where they removed some walls and then add it again. So it's quite interesting game to play with. Next one. Currently, I cannot show you the results because the site investigations are in progress. But from the first information, the masonry used in 86 was with far higher quality than the one in the adding 30, 40 years later. That's why I didn't want to make any calculation yet, because there's such a big difference. We have to find it, and then next time I hope I can deliver you more information. But okay, what we learned from this, some challenges. Well, modeling of unusual structural compositions as 2-ply, I call it 2-ply floor, I don't know, 2-level floor, with alternate direction of load-bearing beams. It's, for me, I don't know how to cope with. I had also a little bit problem with modeling of columns. I must say that I'm not very experienced user. My peer students were much more experienced, so maybe I will ask some of them. I am trying to do something because I have time now myself, and we'll see how it will go on. And also I found that from my side, who am early user, the online help support is quite, in some cases, weak, especially when I want to integrate the roof structure frames. They come some diagnosis which is not very clear, although I follow completely the manual. Also, quite weak online help support is for issues found out from model analysis and kinematic analysis. So I will dig in more and try to resolve, but it could be a little bit more work on these issues. Next one. So maybe on side of help to be a little bit more improved. Also, it would be good to slightly add something else, because very oftenly the timber floors are like it's here on this drawing. They're double planked, and planks are 1 inch. So, and I think it can contribute. So it's very easy for designers to put in. It's a little thing. But then I have 2 other suggestions. Well, I was working about 15 years on the CLT testing, and also in one system which we developed together with the University of Zagreb, CLT frame with the laminated glass, which is very much a load-bearing element. So maybe next slide. These 2 systems could be very well used, especially when you need to replace the inner partition walls and you are limited in dimension. Why? We found out that CLT, 3-ply CLT of typical 10 centimeters, have load-bearing capacity of the quite good masonry wall of 30 or even more centimeters. Technically, it's very easy, and if needed, I have quite a lot of data. We did testing 15 years on this. So here in this reference, there's some things referred, so I would be happy if we can work on this. And also the recent one is published last year, year 2020. It's this element which can be very useful when we need to open some part in facade, but to be load bearing. So since all envelopes and hysteretic curves are very similar to those of masonry but with much, much higher ductility, I think it can be maybe worthwhile to think about this initiative. I was talking with Sergio Lagomarsino because we've been together in one of projects, EU projects, Perpetuate. He said that he will come to me with this. I'm waiting for him. And maybe it could be especially in Zagreb. There are many buildings in the city center where partition walls are damaged. People are not happy to have some structural thing from the basement up, but they could accept something like the CLT. So maybe in future it can be a challenge. Next, please. So let me thank you for attention. And I'm very sorry that I couldn't deliver you more information, but just something about the project in progress. Thank you.
Oh, thank you, Professor Zarnic. Your presentation was really interesting, and finally we got it complete. And I also thank you for all the suggestions you gave. Part of them are relatively, say, easy to implement, and say the definition of equivalent floor for the CLT double plank floor could be could be implemented easily as a user-defined floor, whereas the addition of a new element for the CLT framed and laminated glass element needs some further development, although it is quite say compatible with those with the elements which are already implemented in the program. So I think this is something that could be implemented in the future, in particular if, as you say, this could be of help for specific projects, for specific applications. Thanks again.
Thank you.
And I now pass the speech to Dr. Anna Simões from Lisbon, and she is, as I told you, a researcher, but she also works as a Tremuri representative in Portugal. So please, Anna, the floor is yours.
Okay, thank you very much. I'm not sure if you can see my screen now.
We can.
Oh, good. Thank you. So thank you very much for the introduction, and also to Stadata for the organization of this seminar. So my presentation has this title, Seismic Vulnerability Assessment of Masonry Buildings in Portugal. Okay, now. So this is the outline. I'm going to briefly talk about the seismic risk in Portugal, about the regulation in force right now in Portugal as well, and I'm going to present some case studies of masonry buildings analyzed using Tremuri, and that are being, as well as some work developed in different universities in Portugal using Tremuri as well. So when we combine Portugal and earthquakes, one of the first ideas that come to our mind is the 1755 Lisbon earthquake, of course. Because it's completely destroyed the city of Lisbon, not only because of the earthquake itself, but because of the tsunami and the fire that spread through the city just afterwards. So when we talk about seismic risk in Portugal or in any other location, we have to consider these three components, of course. So the seismic hazard, the exposure, and the vulnerability. So here on the left side, I have a picture of the main tectonic faults in Portugal mainland. So Portugal is located in the southwest part of the Eurasian plate, near the border with the African plate and the North American plate. We are subjected to offshore seismic events and onshore seismic events. In terms of exposure, this relates to the buildings, infrastructures, and people exposed to this hazard. So here we have the view from Lisbon, the capital of Portugal, and finally vulnerability. So here I decided to put this picture from Carmo Convent in Lisbon. This convent was destroyed after the 1755 earthquake, and it was decided a few years after to keep it as it is, as a memorial of the earthquake and the damage that it caused in Lisbon. I'm going to just briefly talk about some of the most important seismic events in Portugal. So again, the 1755 earthquake in Lisbon that also affected the south area of Portugal, the area of Algarve, as well as the north of Africa. And this seismic event is considered as reference for the definition of the offshore seismic event according to our regulation. Also another event, the 1909 earthquake in Benavente, which is a town not so far away from Lisbon, and this event is considered as reference as well for the definition of the onshore seismic event according to our regulation. Another major event, not so many years ago, so the 1969 earthquake that affected Portugal a little bit from north to south, mainly in the countryside area. And of course, talking about earthquakes in Portugal, we have to also emphasize the earthquakes that happened in Azure, the one in 1980 in Terceira, Iceland, and this one in 1998 in Faial and Pico Island, with many damages on masonry buildings. And finally, I could not finish this part without referring this series of seismic events that are happening in Azure right now, since March until now, more or less. So many seismic events, some of them felt by the population. There was also the threat of a volcanic eruption. In terms of damage, there is not a lot of, the records are not significant, but okay, it's just part of our daily news right now, even though things are much more calmer at this moment. Talking about Portugal, mainland Portugal, again, there are many studies that were developed to assess the seismic risk of the building stock in Portugal. This study from Silva all developed in 2015. So there were some estimations of what would be the direct economic losses if an earthquake with a return period of 475 years would have. So it was estimated that the direct economic losses would be about 32% of the GDP from Portugal dating from 2011. It was highlighted as well that the main critical areas were the region of Lisbon and the south of Portugal in the area of Algarve. And that the critical classes or typologies of buildings would be the masonry buildings. It's also important to refer that more than half of the building stock in Portugal is composed by masonry buildings. Okay, so this is the global picture of the seismic hazard and seismic risk that we have in Portugal. Now, in terms of regulation, the first regulation in Portugal that referred the need to consider the seismic action for the design of buildings dates back from 1958. So at the time, in a very simplified way. There were some revisions in 1961 and after in 1983 with a more sophisticated way to define, or more accurate way to define the seismic action and also the analysis methods. And this regulation from 1983 is still in use until these days. However, in 2019, we finally approved the application of the Euro codes in Portugal as the design regulations for the design and assessment of buildings. So we are still in the transition period between the application of both regulations, but this period is going to end now in September. So, but the point here is that until now, or before 2019, there was no legal requirements for the assessment of existing buildings in Portugal. And we have some special regulation for conservation works and rehabilitation works in existing buildings. But even that regulation, there was no consideration regarding the seismic safety of these buildings. So this is the scenario that we have in Portugal at the moment. So this after 2019, in 2020, Stadata had a bigger representation in Portugal with the commercial collaboration with the commercial representation of Tremuri program made by me and in collaboration with Professor Rita Bento from Instituto Superior Técnico. Also because of the implementation of the Euro codes as the codes in force in Portugal, a lot of training courses and seminars started to be presented in Portugal, exactly to transfer the knowledge that for many years has been developed inside the universities, but to transfer this knowledge for the industry, so the awareness start to increase. We can also refer that the work that we have been doing together with the National Organization for Engineers and the National Organization for Technical Engineers, as well the training courses developed and promoted by Fundec, the Advanced Training Association from Instituto Superior Técnico. And I'm also happy to say that Tremuri is right now being used in many universities from north to south in Portugal, that they are highlighted here in this map. So Tremuri is being used in terms of PhD and master thesis research works, final reports from courses, also some publications in terms of national, international journals and conference proceedings. So Tremuri is being used as a tool for the seismic assessment of existing buildings and especially masonry buildings, of course. So I'm going to present now some case studies that have been developed in the last years using Tremuri. The work that has been developed in the Instituto Superior Técnico. So I'm going to start with showing this work that was developed by Helena Meirelles in her PhD research work that addresses the seismic behavior of Bombalino buildings in Lisbon. So Bombalino buildings are masonry buildings that were built in Lisbon after the 1755 earthquake. So these buildings, they have these specific features that characterize their better behavior in terms of seismic action, or at least they were designed with some seismic measures in mind. For example, we have these characteristic interior walls that are defined by a truss timber structure that was then infilled with masonry. And during the PhD work, a very significant experimental campaign was developed exactly to characterize the behavior of this type of walls. And it was also developed a macro element model for the modeling of this type of walls in Tremuri, but in the research version of Tremuri. So this was then used for the global model and analysis of this Bombalino building that was took as reference, let's say. What I can refer now is that we are at the moment developing some work in order to define which parameters can be considered for the modeling of this type of walls, these Bombalino frontal walls, but using Tremuri in the commercial version. So we are calibrating and the parameters based on the experimental work, the experimental results, and we are going to publish these results in the end of this year for this conference that will be held in LUNEC in Lisbon. So something to watch. Another case study is the work that I developed during my research work for my PhD thesis, together with Professor Rita Ben, Professor Sérgio Lago Marcino, and Professor Serena Catri, and Professor Paulo Lourenço. So, well, this work addressed the seismic behavior of Galeiro buildings as well in Lisbon. So these buildings were built after the Bombalino period of construction, and these buildings have, in general, a worse behavior in terms of seismic performance. So that's why we found it was important to address them and see effectively their behavior. A lot of work was done in terms of the global behavior of the buildings, also using Tremuri, the local behavior of the walls, also in terms of analysis of uncertainties, aleatory, epistemic. So the final aim was the definition of fragility curves for this specific typology of buildings. Another work that I'm also happy to present is the work done by Jelena Milosevic, also for her PhD thesis, related with the assessment of mixed masonry reinforced concrete buildings in Lisbon. So these buildings preceded the reinforced concrete structures. And again, here Tremuri was used for the modeling and assessment of different prototypes of buildings that are representative of this typology. Also, some uncertainties were addressed, and finally, the fragility curves representative of these buildings were derived. So more work done with Tremuri and Instituto Superior Técnico. So we have again I have here a picture of the National Palace of Sintra, the work that Professor Rita Bento just presented. And I would also like to refer that right now there are some studies that are also undergoing regarding Montserrat Palace in Sintra, also using Tremuri for its assessment in terms of seismic vulnerability. Okay. Now, I would also like to bring case studies from other universities. I know that I'm already on top of the time, but I would like to highlight this work developed at the University of Aveiro. This work was addressed the seismic assessment of masonry buildings in Faro, a city from the south of Portugal, also with a high seismic hazard and seismic risk. So this work is very interesting because it addresses the behavior of the masonry buildings, but considering the effect of the aggregate. So it's one of the, let's say, research gaps or a topic that is under a lot of development right now, to see how to tackle this type of issue. So it's a work that it's very interesting, and again, it was developed with Tremuri. Another case study, also from University of Aveiro, this regarding the assessment of masonry buildings in Azure Islands. So 2 different prototypes of buildings, also representative of the buildings in Faial Island. So a huge characterization was done, and also some strengthening techniques were addressed and evaluated to see their effectiveness. So, well, I'm going to conclude. So the idea with this presentation was exactly to bring an overview of the seismic vulnerability assessment of buildings in Portugal, and also the research work that has been done in the academia in the last years. There's a lot of information available and can be used as a reference by the industry when dealing with this type of problems. So thank you very much.
Thank you, Dr. Shimos. Your presentation was really interesting, also because you show a set of different case studies, different types of masonry, different application, also in terms of reinforcement. I mean, the strengthening techniques you have presented are really interesting, and also the versatility, the capacity of Tremori to be, let's say, suitable for different type of masonry structures and mixed structures together with masonry, timber, and concrete. This is really very interesting, and also together with the previous presentation, it helps in understanding the capabilities that through the years have been developed within the commercial version of the program and in the research version of the program. The research version of the program needs to be a few years ahead with respect to what is implemented in the commercial version. This is necessarily this way, and but then it works so that the things that are already developed and tested in the research version then now come into the commercial one. Thanks again. I now leave the floor to Dr. Anastasios Tsiavos. He's Greek, but he's speaking from Switzerland. Dr. Tsiavos is lecturer at the ETH in Zurich, and he's going to present a talk with title Synergetic Design, Assessment and Retrofitting Approach for Sustainable and Resilient Communities. Please, Anastasios.
So thank you very much for this honor of inviting me in this very interesting session. Are you all able to see my screen?
We see.
So you can see my
yeah, we can see everything. Okay.
Fantastic. So thank you very much, Professor Pena, for this invitation and Star Data. So good afternoon from Zurich here at ETH. The topic of my today's presentation is going to be about the synergetic design, assessment, and retrofitting approaches for sustainable and resilient communities. So actually, a little bit about my position. I'm a lecturer at ETH Zurich. I'm teaching the courses Seismic Evaluation and Retrofitting of Existing Buildings and Seismic Design and Evaluation of Bridges. I'm a program coordinator of a new CA's program in Seismic Evaluation and Retrofitting at ETH Zurich. So a little bit about my research interests. Basically, they are based on 5 pillars. The first one is about the sustainable and low-cost seismic design strategies. The second is about the synergetic assessment methods for existing structures. The third one is about the sustainable and synergetic seismic retrofitting methods. And I investigate these 3 topics based on numerical methodologies, numerical approaches, and a large-scale experimental investigation. So one part of my research focuses on seismic isolation of structures. Basically, one problem there is that the high installation cost and the resource demanding construction process basically inhibit the application of the existing seismic isolation methods to a wide range of countries and buildings worldwide. Therefore, the question there is, could we reduce this cost by using low-cost seismic isolation methods that use only materials that are locally available or can be easily resourced. And based on that, during my research at the University of Bristol, we developed a new low-cost seismic isolation strategy that is called Pvc Sandwich. It's basically based on a very thin layer of sand that is sandwiched between two PVC layers, and this configuration, this encapsulation of very thin layer of sand particles creates a rolling behavior of the sand particles, and basically this rolling behavior leads to an attractively low friction coefficient that basically enables structures to slide at an approximately seismic intensity acceleration a little bit lower than 0.2 G. And you see here the relevant experiments at the University of Bristol. And basically a little bit about this isolation. Basically, you see we tested a steel structure first on the 3x3 shaking table of University of Bristol, and you see that when the friction coefficient is exceeded by the seismic intensity of the ground motion record, what we can observe is a substantial sliding of the structure with respect to the bottom due to the rolling behavior of the sand grains. We continued that research. We expanded it to masonry structures, and basically what we developed there is a low-cost hybrid seismic design solution, which basically is based on the activation of different seismic response mechanisms for different seismic hazard levels that our structures are exposed to. Basically, what we propose there is to protect the existing masonry building for the design hazard level using steel ties or steel wire mesh that basically prevent the out-of-plane failure, increase the strength capacity of the structure. And then for motions that exceed the seismic design hazard level, what we propose is the sliding fuse mechanism, a second response mechanism that is basically enables this sliding of the bottom of the structure with respect to the foundation due to this sandwich sand layer. And this combined mechanism leads to a seismic protection strategy for various seismic design hazard levels. And you see the application of this technique in an existing masonry structure, the attachment of the steel mesh that should be attached to the bottom and the top of the masonry wall, the steel ties, and basically the test that we did on the masonry structure. You see here large-scale test at the University of Bristol, and the response that is basically for high amplitude of accelerations is basically a sliding response due to this rolling behavior of the sand grains. But apart from that, a very major part of my current research focuses on the synergetic assessment and retrofitting strategies for existing buildings. So what is the motivation behind this work? That many buildings in Europe and worldwide do not comply with modern code provisions and are seismic code provisions that are at the same time energy deficient. The case is that the investment required for the retrofitting of these buildings cannot be easily justified in many cases based on the benefit obtained through the seismic risk reduction of these buildings, and several seismic design and retrofit solutions are characterized by substantial cost and high carbon emissions. So what we think is that there is a need for a holistic and synergetic approach in the design, assessment, and retrofitting of structures, considering their seismic behavior, their energy performance, and their carbon footprint. So what we proposed is first a holistic assessment tool that basically categorizes the behavior of the structure in three different aspects. The first one is what is called the compliance factor, is currently implemented in the Swiss code provisions for the assessment of existing buildings, and it's a ratio of the seismic capacity of an existing structure over the seismic demand that would be needed for the design of a new structure in the same location. So basically, we talk usually when we deal with existing structure, we talk about values of this ratio lower than 1. And based on these values, we can categorize the behavior of the building in several classes that you see over here. This is one aspect of our assessment tool. The second aspect is the energy performance of the existing structure. There we divide the U value of an existing structure through the U value for a new structure. And basically what we propose is a similar categorization with respect to the corresponding energy performance of a new structure. And we can see how our structure compares with respect to the U value and the heating demand of the structure. And the last pillar of this assessment tool is the embodied carbon emissions basically the retrofitting or the assessment technique, where we can assess what is the environmental impact of our retrofitting with respect to the CO2 equivalent per square meter. According to these classes, we can illustrate the energy behavior of the building at the current state, after also the implementation of a synergetic retrofitting strategy that you see with the gray line, and also after a low carbon synergetic retrofitting strategy in which this spidergram shows good behavior in three aspects at the same time: high rating in seismic behavior, high rating in carbon footprint, high rating in energy performance. This is our goal, to increase the behavior of the structure, not only in one aspect, but at three aspects at the same time. So what we try to do is simulate the behavior of a URM, unreinforced masonry case study building in Switzerland, located in Sion with the highest seismicity. And you see the building over here. Basically, it is a building that is seismically vulnerable based on the three-story building with weak floors, timber floors. And what we try to do is simulate this building with Remuri. And you see here the model of the building. We use the commercial version for the simulation of the in-plane seismic behavior of the building that you see over here in the model. And what we try to see by subjecting the building to a pushover analysis is, at least in plane with different load combination, we try to see what is the fundamental failure mechanism, what is the strength capacity, the displacement capacity of the building. We found these base year values for different horizontal displacements. And of course, we illustrate here the first year failure on this wall based on the concentration of stress in this wall due to the weak diaphragm function of the building. So in order to improve this efficiency of the building, we try to propose some solutions that actually can lead to the improvement of the current behavior of the building. And you see over here what we proposed is a solution that is based on the increased diaphragm retrofitting of the building with a low carbon concrete addition on the top that you see over here. Basically a concrete, the 6 centimeter thick concrete layer is added. The concrete is defined as low carbon because it consists of granulates from demolished buildings and recycled steel. And what we found out there is that this can effectively increase the shear capacity, the strength capacity of the building. As you see, the different diaphragm retrofitting solutions we tried vary from the timber retrofit case of the same thickness, let's say 6 centimeters, that leads to also some increase in the strength deformation of the building, strength capacity of the building. Then with the green line, and then with the red line, we see the red solution of the retrofitted building with a low carbon concrete that led to a substantial increase in the shear capacity of the building. And then we compare everything with a pure concrete solution, which means that we replace the timber beams with the concrete beams, and we see how what would be the shear displacement pushover curve of the building. And in that way, the commercial version has proved to be very efficient of simulating retrofitting solutions of varying materials and thicknesses. So the second solution that we proposed is that emerging from the fact that one big part of the energy behavior of the building depends on the walls and the heating losses due to the poor energy performance of the walls. And what we try to do there is propose a novel solution with timber beams that are infilled with bio-based materials, bio-based panels. We tried several bio-based solutions such as natural grass panels, for example, and we combined this by attaching timber beams to the facade of an existing masonry building. We infilled these timber beams with bio-based thermal insulation materials with attractive thermal insulation properties and at the same time low carbon footprint, and we try to measure what the result is. So this was a part of a collaboration with Dr. Stelios Kallioras this semester. Basically, we co-supervised a master's student at ETH Zurich, and of course, we used the research version of Tremuri to simulate the out-of-plane seismic behavior of the building before and after the retrofitting, using you see this model on the left for the unretrofitted case, and this movement of these models on the right for two different variants of timber beams, one with more timber beams, two vertical and two horizontal, that were simulated using elastic beam elements, and another variant two with less timber material with only one vertical element. And you see that by doing this, basically, what the result is that we managed to reduce the heating demand, and therefore the annual operational carbon emissions of the building substantially due to the use of the bio-based insulation, more than 20%, as you see over here, with both retrofitting variants. At the same time, due to the use of bio-based materials, we can achieve negative carbon footprint values. You see here the negative carbon footprint values for the two variants that basically create an attractive behavior in terms of environmental impact. And of course, the most important element, the improvement of the seismic response of the building out of plane due to the activation of these timber beams that we managed to model in Tremuri. And you see here the ground motion excitation, the displacement out of plane at the top for the unretrofitted case with the black line, and then the displacement that was reduced using the retrofitting timber beams using the two variants. You see the different evolution through time. We managed to reduce the displacement of the building. And if we view the results in terms of a NIDA curve, by scaling the ground motion intensity and measuring the top displacement levels, we can see the substantial reduction of the maximum displacement of the facade of the wall, at least for the two retrofitting cases that were investigated in this study. And you see here the maximum displacements and the reduction due to the two different retrofitting cases with the red and the green line. So what are the conclusions of this work? Basically, what we presented here is a synergetic seismic and energy retrofitting strategy that leads to substantial improvement of the seismic and energy behavior of existing URM buildings using low carbon footprint materials. They presented a hybrid seismic design strategy can lead to the low cost and sustainable seismic protection of structures for various seismic hazard levels in developing and developed countries using materials that can be easily resourced. And this numerical simulation is the challenge in plane and out of plane seismic behavior of the URM buildings, critical for the assessment of the efficiency of the presented strategies. Tremuri was very efficient in capturing this in plane and out of plane behavior in that sense, using the timber bags and the different diaphragm retrofitting strategies that I present. And as the end, my vision for civil engineering focuses on the development of performance objectives for our community subjected to climate change. There is also the energy crisis at the moment, deterioration processes and natural hazards, what we expect the people, the infrastructure and the economy to do. Within this frame, the development of this sustainable design, assessment, and retrofitting strategies that are based on the state-of-the-art of engineering practices and computational techniques lays the foundation for the implementation of this multi-performance synergetic research approach. And along this line, my research aims to offer a new multi-performance and synergetic assessment and maintenance paradigm towards the development of sustainable and resilient communities. And with that, I would like to thank you very much for your attention and for the honor of inviting me in this session.
Oh, thank you, Anastasis, because of your contribution is really valuable, and I think in this case special and unique in the panorama of the speakers. And also, I want to thank you in particular for two aspects that are part of your presentation. One is definitely that you have shown the use of Tremuri in an advanced research project with an important goal. Important not only from the specific research purpose, but also for, I think, the economy and the future of our countries, in particular in Europe. The second reason why I'm thanking you is because you are implicitly stated and remember that seismic safety is part of sustainability. I mean, we have to remember this, that this is an important consideration, that the seismic classification of buildings is not less important than the energy classification of them. And looking at things together is a very interesting and important, let's say, viewpoint and a way to focus properly the situation. Thank you again.
Thank you very much.
I would stay with the Greek presenters, and I give the floor to Mr. Georgios Papadopoulos, who's going to talk about significant masonry buildings in northern Greece. And I think this could be also very, very interesting, and showing us other types and different types of buildings that could be of interest for all the participants.
Thank you very much, Professor Pena, for the introduction. Are you able to see my screen?
Yes, we see the PowerPoint. We don't see the presentation. Okay, now it is the presentation one. Okay.
Okay, thank you very much for the introduction once again. Good evening, everyone. My name is Georgios Papadopoulos, and today I'm going to hold a brief presentation about some of the most important and demanding projects that we designed in our company in the field of masonry structures. Today's agenda begins with some information about myself and the company, and continues with the presentation of 3 case studies that we designed in our office. The first one being the St. Nicholas Monastery in Portolagos, followed by a block of flats at the Karoloudir Street in Thessaloniki, and concluding with the Roosevelt Building, also located in Thessaloniki. I got my diploma in structural engineering from the departments of civil engineering and the Aristotle University of Thessaloniki. After that, I completed a 2-year master program at the Karlsruhe Institute of Technology in Germany, which gave me the opportunity to deepen my knowledge in masonry buildings, especially because my master thesis was in the field of them. And it is worth noting that this was also the first time that I encountered Tremuri during my studies. Following the completion of my studies, I returned to Greece, and parallel to my working life as an engineer of the praxis, I'm also enrolled as a PhD student at the Aristotle University of Thessaloniki in the field of structural dynamics for stone masonry. A few things about our company. It is located in Thessaloniki and was founded by my father back in 1989, and is an office for both public and private projects. Among other fields of structural engineering, we also specialize in the design of steel structures and especially the value engineering and cost of optimization of them, as it is very important today due to the high cost that the materials saw due to the crisis. To begin with, I'm gonna talk you about the West Building at the Portolagos Monastery of St. Nicholas, which is located in Vistonida Lagoon. The building I'm going to talk about is the one that is to be seen on the bottom left corner, as it was originally built back in 1910. Tragically, due to a fire in the mid-1950s, it was burned to the ground, and after that it was completely redesigned, but this time as a one-story building, as is to be seen in the middle picture, from the remains of the old structure. It is very worth to note that this monastery belongs to the Vatopedi Monastery in Mount Athos, and this makes this very significant for its location and its history. Our scope of work in our office was to design the one-story building in Tremuri and to propose if it was possible to add the second story and the roof from the original design, and to make some changes in the original plan of the ground floor. The next project I'm going to talk about, as mentioned before, is the Karolou Dil block of flats, which is located at the corner of Mitropolio Street and Karolou Dil in Thessaloniki. It was built in 1924 as a two-story building, and the rest of the floors were added in 1938. The project that we designed in our office was a private project and was the reconstruction of an apartment located in the second floor of the building. The scope of our work was to check in conjunction with the architect if the demands of the client, meaning that he wanted some openings, some strengthened bearing elements, and etc. We tried to see if his demands were to be met. Due to this, we had, of course, to redesign the whole building and implement it in Tremuri. As you can see, it is a very demanding building, not only geometrically, but also because due to its history that it was built in different times, many materials and different materials and classes were used. Luckily, because to the techniques that Tremuri offers, we achieved to meet the demands of the client. Here you can see in the previous slide some of the pictures during the construction phase and some of the specimens that were taken in order to check the classes of the materials. The last project I'm gonna show you is also the most iconic one, and that is because I kept it in the end. It's called the Roosevelt Building, and it's located at Eleftheria Square in Thessaloniki. It was built during 1926 and 1927, and it originally belonged to the Ionian Bank Limited. It is a very iconic building for Thessaloniki, and its use changed during the years. During the war, it was used as the headquarters of the army, and after that, the Ionian Bank was absorbed by Alpha Bank, and very recently the whole building was acquired by an individual, so I cannot reveal more about its future use as it is the wish of the customer. The scope of our work was to model and analyze the whole building and propose a retrofitting program. The work is still in progress. The building in itself is very complex, not only because of its geometry, but also because the large number of materials that were used. on the ground, on the basement, we see concrete blocks that go all way to the second floor. The very peculiar thing is that these blocks made of concrete contain stone taken from rivers as aggravate, but also rough stones mixed with the cement, and there is no reinforcement to be seen. Continuing to the inner of the building, we can see the normal reinforced concrete elements, beams and columns. And it is very complex because, as you can see here with my pointer, there is an atrium. The mid-floor is supported on very large beams that are to be seen here. The center slab is a composite slab made of steel elements, masonry blocks, and filled at the top with concrete. The materials are very scattered, so we have an ongoing research process in order to define the classes. The nodes, the original design nodes, and the drawings that we found differ from each other during the phases. Many beams and columns were not shown at the last designs that we found. So we have to make a very extensive research program in order to be sure that the demands of the client are going to be met. Luckily, even though this process of the research for the materials is still ongoing, we have finished with the geometry of the building. So you can see here how it is developing from the basement till the top floor. Without Tremuri, it was not going to be able to design this. So Tremuri was once again, as before, the only way to go for this project. So to conclude with, I would also like to mention that all of the three projects that I've shown earlier were subjected to earthquakes during their history, some of them minor, some other major. But what is worth mentioning is that their pathology is very, very, very limited. So this makes us wonder about the capabilities of masonry, stone masonry, masonry walls. And that is because the research that the universities carry is still ongoing and very interesting. Last but not least, I would also like to thank the organizers for letting me hold this presentation and the local distributor ErgoCAD for the effortless and continuous support that we get during every project. At that point, I would also like to thank you and wish you a pleasant evening.
Thank you, Georgios. I think that everybody has appreciated very much all the different cases you have shown and the difficulties that have been solved in the issues that have been solved using Tremuri in all these specific cases. And also together with the previous case, I mean, I think that we can cover many of the different differences that can be found within the European building stock that offers certainly a large variety of structural solutions implementing what we call together masonry structures, but actually this definition of masonry structures means a number of very different things. Thanks again. I think that now we have the intervention by Jacopo Scacco just to interrupt the series of Greek presenters.
Hello everyone, I am Jacopo Scacco. I am PhD specialized in Masonry structures, and now I am an analyst software in Stadata. Today we will talk about the module arch that is present in Tremuri project. We will talk about it and its future updatings, and we will talk about the theories that are behind this module. Let me recall briefly what there is behind what is Tremuri project. It's an integrated software that allows a global analysis of the structure and local analysis of the structural elements themselves. In particular, today we will talk about the module arch that is already present in Tremuri project and will be soon updated. Let me cite this proverb that should be Indian. I'm not sure about this. An arch never sleeps. And this, in my opinion, explains in few words the beauty of the structural element arch. Because for an arch, in order then it maintains its functionality, it's necessary that each element, each stones of the arch plays its role. The arch is able to sustain the external loads by an internal distribution that follow a path. This path is called the thrust line and is a polyline that connects each resultant point of the compressive force acting on each interface. So the arch is able to sustain external load only under compression. As I told you, we have already arch in Tremuri project, will be soon updated. It provides a wide range of features, tools, and possible analysis. I wanted to remark that it is possible to analyze arches with any different shape, and it is important. It will be possible to analyze the arch in its reinforced scenario and reinforced scenario with composite materials like FRP and TRM. Then the user can choose a wide range of analysis, starting from static analysis that basically provides the thrust line and much more, then we will see. And then we have cinematic analysis, where the main output is the collapse mechanism and its relative multiplier. But in this case, the analysis is provided both for static and seismic loads. Concerning the seismic loads, is also available a nonlinear cinematic analysis that put at disposition of the user the evolution of the collapse mechanism. I want to highlight that all the analyses are performed according to Eurocode 8 and the NETC Italian code. This presentation is done also for showing you which is the theory that is behind this module arch. The theory that is behind is the classic theory of limit analysis that Heyman found out was applicable also for masonry structures. Indeed, the problem of the arch that is only apparently a simple structure, the arch has been studied since centuries from scientists, architects, engineers, starting from Hooke, citing Coulomb, Mascheroni, Méry, until arriving to Heyman. Heyman stated that this classic theory of limit analysis that they were used to be applied to steel structure were also successfully applicable to masonry arches, only if some specific assumptions were ensured. What I mean, the masonry has no tensile strength, so it's a notation material. The compressive strength is considered unlimited. This what does it mean? It means that usually the level of compression of stresses on masonry structure is low compared to its compressive strength, so we can consider this unlimited. And then, this is important, the sliding failure does not occur. We don't consider sliding failures in arches. The first theorem of the classic static, the classic limit analysis, is the Safe Theorem, or we can call it the static approach. What does it mean? It means that if we have an external load and the arch is able to respond to this external load with internal forces that are in equilibrium with external load, and are bounded within certain limits. In the case of the arch, the limits are the border of the arch itself. If we are able to find this internal distribution of stress, that external load is a load that is for sure lower of the real collapse load, or at the maximum is equal. So in another way, this is the reason why Heyman called this the safe theorem. The structure is safe if we are able to find this internal distribution. This is the static theorem. The safe theorem is at the base of the first analysis that is provided to the user in our module arch. That is defined as thrust line analysis. This module permits to obtain the optimized thrust line. When I talk about optimized thrust line, I need to make a step back, because the arch is a redundant structure. So this means that the number of solutions of thrust line that we can obtain is infinite. So what we provide to the user is the optimized one, that is the thrust line that minimizes the distance between the medium line of the arch and the thrust line itself. It's a very useful tool because it's a very fast way to notice the location that might suffer damage, and it's a fast way to understand the safety state of the arch. There is not only the thrust line as main output. First of all, it will be possible to input pre-existing cracks. And this is obviously very noticeable, I would say, because when we treat a real arch, the cracks are often present. Then it will be possible to plot internal action and internal stresses along with the thrust line, and it will be as main output present also the thrust at the springs. And this is fundamental when we want to make a computation, for example, considering the autoplane of a wall, or if you want to design a tie. And then, last but not least, there is a list of safety factors that are related to geometric consideration. That is a ratio between the eccentricity and the height of the arch itself. And then there are safety factors that are related to the mechanical properties, so namely to the compressive strength of the material. Now let's talk about the kinematic limit analysis, that is the twin of the static approach of the classic theorem of limit analysis. In this case, we assume that the arch has a collapse. So we need to assume a collapse mechanism. And in order to get the value of the external load that lead to this collapse mechanism, we need to put equal to 0 the work of the external forces. The load that we obtain from this procedure is a load which value is for sure measure of the actual ultimate load, or at least equal. I want just to remark that in the case of the arch is, as I already mentioned, a redundant structure. It's a 3-time redundant structure. So in order to obtain a mechanism, we need to impose 4 hinges, at least 4 flexural hinges. In the case of an arch loaded symmetrically, we need, in order to have a collapse, 5 flexural hinges. This is the theory. Now let's see what the modular arch give to the user in terms of cinematic analysis. The main output output of the cinematic analysis is the real mechanism collapse. This is thanks to a very fast and efficient iterative procedure that the software does in order to provide to the user the real collapse mechanism with the correct localization of the hinges. I would say that the power of this analysis is the possibility to explore the maximum capacity of the arch in few seconds. Furthermore, it is possible to input pre-existing hinges. When I call hinges, I mean crack completely developed. Then, as main output, the user, we will see the thrust at the spring immediately. And then, for relating to the seismic analysis, so under horizontal load, it will be possible to consider the seismic contribution of the filling and the variable loads. And then, this is remarkable, it is possible to run the analysis on reinforced configuration in static and under static and seismic loads. Let's conclude the theoretic part of this presentation citing the uniqueness theorem. The uniqueness theorem assesses that if you are able to find a thrust line that is internal to the arch, so this means it's an equilibrium state, but this thrust line touches the arch in 4 different points, so this leads to a mechanism, that thrust line is unique. With our software, with our module arch, this is possible. When you are going to compare the results by using the static approach, by using the cinematic approach, you will be able to get the unique thrust line. And this is important because it's sort of internal validation of the software. Let me conclude with this last slide that I mentioned in the first slides, and it's related to the possibility to run nonlinear cinematic limit analysis. When with this nonlinear, I mean that it's possible to track the evolution of the collapse mechanism under seismic loads. So we have the safety factors that in this case, they are in terms of displacements, and the user can visualize the graphic evolution of the collapse mechanism and the evolution of the collapse multiplier. Even in this case, like before, it is possible to perform analysis on reinforced configuration. With this slide, I finish this presentation. I hope that it was interesting to talk about arch in general and in particular of our module arch that I want to repeat. It will be soon updated. So thank you again for the attention, and I leave the desk to the next speaker. Thank you.
Okay, thank you for this interesting contribution. Jacopo, I think, is online, or even if the...
Yes, thanks, Professor.
Yeah. Thank you, Jacopo. Your presentation was really clear, and I think you have presented an interesting new addition to the Tremuri project package, and I think that the development could be also further, and this is a new interesting feature. Then I think that we can now continue with the Greek speakers. We go to Stylianos Kallioras. He is Greek and a little Italian because of this.
Yet
adopted,
exactly.
And Stelios has been one of my PhD students. He did his MIS masters in Pavia, and his PhD at the Rose School in Pavia.
Yes, correct. I've been working with Professor Penna for many years, and I've done a lot of research using Tremuri. So today I'm going to present you a case study on numerical assessment of the seismic behavior of Masonry buildings subject to the 2012 Emilia earthquake. This is a case study carried out a few years ago under the supervision of Professor Penna, Professor Magenes, and Dr. Paolo Morani. It was carried out using the research version of Tremuri, the so-called academic version of Tremuri. Tremuri is under constant development, and some of the features of the research version hopefully in the future will be implemented also in the commercial version of the software. So a few words about the study I'm going to present. The study was motivated by post-earthquake observations of damage on buildings that on Masonry buildings, modern Masonry buildings that were not designed.
Sorry, Stelios, sorry for interrupting you. Can you share your screen? Yeah, because.
Yes. A second.
Yep.
So screen.
Okay. We see, I guess, your desktop. We see a macro element drawing. Okay.
Now you see the.
Yeah.
You see the presentation, right? Okay.
Yes.
So yeah, the study was motivated by post-earthquake observations of damage in modern Masonry buildings that were designed with no seismic considerations. A set of buildings was selected for detailed investigation. We did some seismic verification studies applying the current standards, the Italian standards, the European standards, and we noticed that maximum obtainable peak ground accelerations resulted significantly lower than the shaking that the buildings, the case buildings experienced the site. The 2012 Emilia earthquake gave us the opportunity by providing a unique damage data set to model the seismic behavior of real buildings and to quantify the conservatism behind the current code design procedures. So the study was articulated in many different phases. At first, we developed. Do you see my screen? My presentation? Yes, because my computer crashed. Do you see my presentation? You confirm that you see my presentation, right? Okay. So first we developed numerical models to carry out simulations of the earthquake scenarios, of different earthquake scenarios for the 2012 Emilia earthquake. Then we performed a fragility study based on existing analytical model-based procedures. We conduct a reliable probabilistic seismic performance assessment accounting for uncertainty in both structural capacity and demand. And in the last step, we attempted to evaluate the safety margin provided by the current building codes. In this presentation, I will focus mainly on the first two phases of the work, which were centered around using the Tremuri software. So for the development of the study, we used the equivalent frame modeling strategy. Where possible, we adopt experimental data to update our models. We validate the models using empirical data by performing simulations of earthquake simulations, and we derive fragility functions using state-of-the-art procedures. In this case, we selected three real buildings from which are located in the province of Modena. Two of these buildings, after the earthquake of Emilia, didn't suffer any damage, while the third one results significantly damaged. And if I'm not mistaken, it was also demolished. Here you can see some of the damage observed in the third building case, which was severely damaged in the front and rear facades, which was also the weaker, it was a weak building direction. For our modeling purpose, we use Tremuri, the search version of Tremuri. Tremuri has been successfully used in numerous studies in the past. It has proven that to simulate with reasonable accuracy the dynamic response of entire buildings. We adopt the frame type representation of the in-plane response of walls. The out-of-plane response was not explicitly accounted in this case. Such an assumption was considered acceptable for the analysis of these buildings, where rigid diaphragms and low wall height to thickness ratios render the out-of-plane response a secondary concern. Each wall is modeled by assembling pierced spandrel beams represented by two node macro elements connected by rigid nodes. This is the nonlinear macro element model developed by Professor AdriaBIM and Stefano Bracchi. It has been improved significantly in recent years. The macro element is divided in three parts: a central body, where only shear deformations are possible, and three interfaces, where external degrees of freedom are located and permit axial deformations and rotations with respect to the extremities of the central body. The flexural rocking response of the panel is represented adopting a unilateral contact model. Zero length springs are located at the interfaces. They follow a bilinear constitutive model compression with no capacity tension, allowing this way the explicit evaluation of how cracking affects the rocking motion. The model includes a nonlinear path for rocking behavior that accounts for the effect of limited compressive strength. The rule is characterized by an unloading branch with a slope equal to the initial stiffness, thus allowing increased energy dissipation and the ability of modeling deformation accumulation. The shear response of the panel is modeled through a constitutive law expressing a nonlinear response, a nonlinear relationship between shear stress and relative horizontal deformation, as you can see on the plot on the left, on the right. The lateral strengths provided by the shear model results from the application of the equivalent Coulomb type criterion with parameters suitably calibrated, being macroscopically representative of the shear failure modes with the diagonal cracking through bricks or stepped cracking with sliding along the joints. The mechanical properties of the macro elements were updated from in situ tests. We performed some in situ tests for the determination of the mechanical properties of the masonry. Where possible, experimental information was also past experimental information was used. The macro element mechanical properties were based on mean values of the material properties. Drift limits were defined after statistical processing of experimental data, and the phenomenological parameters of the macro element were defined after model calibration against in-plane quasi-static cycle tests performed in the lab. We performed some pushover analysis to identify potential damage mechanisms and the most vulnerable parts of the buildings. For example, this is the first building that didn't exhibit any damage. You can see that the resistance of the building in the longitudinal direction is significantly higher than the transverse one due to wider piers and greater gravity loads. This is due to the orientation of the floors. By the way, I missed to mention that in all three building cases, the diaphragms are rigid, they are reinforced concrete slabs. And everything was also the presence of ring beams. This is the third building case, the building that exhibited the damage. You can see a soft story mechanism, the first story, significantly lower lateral resistance on the building direction that exhibited most of the damage. With this pushover analysis, we later will define damage limits, consulting also criteria in the existing literature and in the norms. Based on these limit states, we later proceeded with performing fragility analysis. To carry out the earthquake simulations, unfortunately, we didn't have many available recordings. We had to generate recordings using different methods. We came up with around 15 earthquake records generated through stochastic ground response analysis with modification of Sergan's Gordon at the nearby seismic stations after using spectral matching techniques. And we also use some synthetic accelerograms generated using seismic source and earth crust models. We performed dynamic analysis, time history analysis. In most of the cases, as you can see here, we saw that the analysis results confirm what we saw in reality. This is building case 1. In almost all cases, the building results with 0 damage. Only in a couple of cases that the seismic input seems to be a bit overestimated. The model showed that the building manifests some slight damage. In building case 3, though, in almost all analysis, the model shows that the building suffered significant damage in its vulnerable direction. We perform Monte Carlo simulations for the generation of population of building models. The geometry was treated deterministically, while uncertainty was introduced by varying mass mechanical characteristics that present significant variability. We also varied some drift limits for failure in shear fracture and the vertical loads carried by the Mason piers. I will not enter into details. We perform around 1,200 pushover analysis for each building direction. On the generated pushover curves, we identified damage limit states based on the criteria we discussed before. These limit state variables were summarized into an estimate of a central value and a measure of dispersion, and were approximated by assuming suitable parametric distributions, in this case log normal distributions. Using the earthquake accelerograms that we saw before, we performed incremental dynamic analysis to come up with probability distributions of displacement demands. In our analysis results, we saw that the greater was the dispersion due to the record variability, while dispersion in displacement demands due to uncertainty in structural modeling parameters was really small. Fragility functions were later derived by folding together probabilistic representation of capacity and demand using state-of-the-art procedures available in the literature. I will not enter into details. Let's take a look at the results. Starting with building case 1. The building appeared to be weaker in the north-south direction. This because of, as we said before, orientation of the floor. So in the longitudinal direction, vertical loads sustained by the piers were greater. So greater was also the lateral resistance. Wider piers, while in the other direction we had wider openings. Based on the fragility analysis results, this building should suffer with relatively high probability slight structural damage in its weak direction. In reality, we didn't see any damage in the building. Building case 2, also here, the fragility analysis showed some damage in both building directions, despite the fact that there was no damage in reality. This building was significantly more resistant in both building directions with respect to the other 2 building cases. And this is building 3. The fragility analysis actually predicted damage in the weak building direction on the structure. In most of the cases, it's near collapse conditions, while only slight damage was predicting the strong building direction. So after conducting this study, we predicted the models predicted quite accurately the damage seen in building case 3. Building 1 and 2 appeared slightly weaker compared to the observed seismic performance, but this conservatives, the analysis results most probably attributed to overestimation of the effective intensity of the seismic motion that we employed. Maybe possibly conservative assumptions on in the adopting material parameters, and the adoption of strictly defined damage limits or low ultimate drift limits associated with in-plane shear failure modes. Nevertheless, the study showed that tremuri can be effectively used for probabilistic analysis using high quality data and seismic input. The models in this case were validated with real earthquake observations using the empirical data from the Emilia 2012 earthquake, and the results are quite promising for similar studies of this type, for seismic vulnerability studies, seismic risk studies. Can be performed relatively fast with low computational effort and with quite high accuracy and reliability. Thank you very much for your attention. If you have any questions, I'm here to answer them.
Thank you, Stelios. I think that your presentation has I would not say something about the things because I know what is the work behind, but I think that it is very important to see how the tools we use have some degree of conservatism, or how do they compare to reality or to experimental test. And in this case, I think that the more advanced version of the program, the one with less conservative inside, is slightly conservative still. So this is something that from one side tell us that what we use normally provides some extra conservatism with respect to what we assume when designing, but from the other side it also tells us that maybe we should go a little further towards the use of more advanced tools and to introduce more advanced features to be less conservative and to be closer to reality. Thanks again. And last but not least, the only Italian speaker, Marco Tondelli. Marco Tondelli is one of my former master students. He is the first man in the world running more than 1 million pushover analysis in a single master thesis. I think that he managed to share his screen, and the topic of his presentation is modeling timber-based strengthening for URM buildings, but the application is not Italy. It is on building in the Netherlands. Please, Marco.
Thank you, Andrea, for the introduction. Can you hear me?
Yes, we hear you.
Okay. So, well, first of all, thank you, Stadata. I want to thank Stadata and Professor Penna for inviting me. As Andrea said, I'm a consultant in the field of earthquake engineering, and I collaborate with an Italian company which is based in Pavia. It's called Seismic 360, which specializes in the seismic assessment and design of structures, especially unreinforced masonry structure. And my presentation falls into the framework of a collaboration that Seismic has been running since 2018 with a Dutch partner company, which is called A-Construct, and I would like to take the chance to thank them as well. This collaboration focuses on the seismic assessment of structure which are based in the Groningen region and which are subjected to induced earthquake. As many of you may know, well, the Groningen region is located in the northeast of the Netherlands, and is quite peculiar because there is a seismicity induced by gas extraction. The earthquakes over there may be not major earthquakes, as we can be used to, for example, in the case of tectonic earthquakes. The problem there is that the structures are particularly vulnerable, since the structures over there are designed only to withstand static loading. So over the last, I would say, more than 5 years, there has been a huge engineering effort toward the seismic assessment of the vulnerability of existing structure and the retrofitting of existing structure. I think it's also important to underline the fact that due to the peculiarity of the problem, the engineers in the Netherlands should use a specific guidelines. So over there, we don't use the Euro Code 8, but a specific guideline has been drafted, which is called MPR 9998, and is specific for the seismic assessment and design of structure which are located in the Groningen region. Another important thing to underline is that this guideline was first drafted in 2015 and underwent several modifications over the years. The actual version is the 2020 version, and over the years we observed quite a significant increase of the displacement capacity of structure when analyzed with the nonlinear analysis, pushover analysis. On the other hand, we have that the seismic input of the region is defined starting from, here we see the web page of what is called the MPR web tool, and also on the input side there was a significant variation over the years. Why? Because the extraction of gas was reduced, so also the seismic input was reduced. It did not reduce evenly on all the region, but there was a more significant reduction in the peripheral areas. So the peculiarity of the Dutch problem right now, of the Groningen problem, is that the same structure assessed like 5 years ago or right now would have a quite significant different outcome due to, on one side, the increase of the capacity, and the other side, the decrease of the demand. As we have seen at the beginning in the presentation from Stadata, well, the Dutch guidelines are included in Tremuri in the commercial version. So here today I'm presenting results about the commercial version of Tremuri. So you can see in here that the NPR 9998 is included in the Tremuri commercial software. I would like right now to underline some peculiarity of these guidelines, especially because many of us, as Europeans, we are used to Eurocode. So there are some differences which are bigger from the NPR to the Eurocode. First of all, there are 3 failure mechanisms for Meso repair. So shear failure for the joints, shear failure bricks, and flexural failure. What is important to underline in here is that these 3 mechanisms are associated to drift limits which are significantly higher than the Eurocode 8. For example, the shear failure in joints is associated to a 0.75% against what is 0.4 in the Eurocode, whilst the shear failure in bricks and the flexural failure, they have a variable drift limit, which is generally never lower than 1% and can reach up to 2%. So you can understand that the displacement capacity which we can obtain over there is significantly higher, also because we assess structure at the near collapse limit state, not at the significant damage. Another point is that for shear failure, the NPR 9998 underlines that both sections of the so the top and the bottom section of the Meso repair should be verified. Another big difference is the bilinearization of the pushover curve. I would say the major differences are 3. The first one is that the intercept for the definition of the period is at 0.6, the shear capacity. The second major difference is that the ultimate displacement capacity is defined at the 50% drop of the maximum shear. So it's a significant difference with respect to the 20% drop that we have in Eurocode. And the third thing is that the equilibrium of the area is performed considering the displacement at 80% drop. So we also, in terms of bilinearization, we push a lot the capacity. Then other differences that we have are, for example, the possibility to take into account the soil structure interaction, which translate into an increase of the displacement capacity of the structure. The use of gamma factors, so the transformation factor from a single to multi-degree of freedom equal to 1 for structure which are 2 stories or lower. And then another important thing is that the Dutch guidelines underline that the structure, the seismic assessment should be performed with the capacity spectrum method. Now it's important to say that this method was originally conceived for the design and not for the assessment. So there are some issues, I won't go into detail in this presentation, but there are some issues when using this method for the seismic assessment. Also, there is the possibility in Tremuri with the Dutch guidelines to use, well, the N2 method. We are all familiar with that, but also with the modified N2 method, which was developed at the University of Pavia by one of the postdoc of Professor Andrea Penefnotong, Dr. Guerrini, which is called the modified N2 method. This method basically corrects for the fact that usually with N2 methods we tend to underestimate the displacement demand for really short period structure. So these are, I would say, the main point to underline about the Dutch guidelines, and all these points are integrated into the commercial version of Tremuri. As I said, the structure in the Groningen region, they are quite vulnerable, and they are quite vulnerable for several reasons. For example, they have big openings, they have cavity walls, so double walls with void between the 2 leaves where the outer leaf is non-structural, and they have some of them quite peculiar configuration due to the fact they are agro building, so farm building. The most common retrofit measures, well, they are really varied. One retrofit measure that I've seen is basically not retrofitting, but demolishing the whole structure, especially if it was in bad condition of restoration. We can see a picture in here where only a facade was kept and then the building was turned into a timber structure. Adding HSB, stiffening the floor or the diaphragm, adding HSB walls. This measure can be used either to, let's say, improve local failure and global failure, and also a quite typical solution over there, which is quite local, is this quake shield solution, which is adding carbon fiber strips, cutting slots into the masonry, and then you can either well, add them also with some reinforced plaster just to prevent the out of plane failure, or you can anchor them into the slab and the foundation if you have the case, and in that case you can also improve the in plane capacity of the masonry pier. Here today I will present a simple case study, well, very simple compared to the really big structure that we have seen before from the other speakers, and it's just a simple case where I want to show you how we have implemented in the commercial version of Tremuri the retrofitting of a structure with timber shear panels. So you can see the structure is very basic, 1 floor, square footprint. We have a second floor, but is enclosed by the pitched roof, so we have no structural masonry over there. We have 210 masonry walls on the perimeter, a main inner wall 100 millimeter on the, let's say, Y direction, no structural walls internally in the X direction, and this is the spanning of the diaphragm. Diaphragm can be considered as rigid because there was previously already a stiffening intervention with USB panel. So we perform the seismic assessment using the capacity spectrum method in the actual condition of the structure. And first of all, I would like to underline, as I said before, that due to the code as it is, we can obtain significantly larger displacement capacity for the structure. So if we run the analysis, we obtain this point, 42 millimeter, as ultimate displacement for the structure. The truth is that particular attention must be paid by the engineers if there is local stability or collapse of some elements which can trigger local collapse of the structure. For example, in this case, we can see this pier in here on the right-hand side, which corresponds to this corner in here, which is actually collapsing at this point. And so we stop the analysis over here because we consider that the failure of this element well could trigger local collapse of the roof, since the roof is supported by the perimeter walls. So particular attention has to be paid when using this code, especially because it's pushing a lot the capacity in terms of displacement and to the 50% drop. We can also see that the drop in here corresponds to more than 20% drop with respect to the maximum shear capacity. So these results are more in line with what we would obtain with the Euro code. So finally, we can see that in the X direction, the structure is not verified. So we need to strengthen the structure, while in the Y direction, since we have quite a lot of walls, the structure is safe. Okay, here we have a zoom in of the results. As I said, the idea is to actually use timber panels to improve the seismic stability of the structure. So the idea is to replace 2 non-structural walls with the new Hsb walls that will be properly connected to the foundation and to the existing diaphragm, and then to change the internal configuration of the structure on the left-hand side, adding a new Hsb panel. This will allow us to have enough length of panels to resist seismic forces. So the interesting thing in here is how to model this panel. There is a MSc dissertation which explain how to account for this Hsb panel. So basically, the timber panel is turned into an equivalent element, equivalent frame, you can say, where we have some rigid element hinged at the extremities that they define the geometry of the panel, And then we have a diagonal, which is actually the element that controls the lateral stiffness and strength of the panel. The definition of the diagonal depends on several factors. The most important, well, this is the formula. The most important are the fasteners. So if you use nails, screws, the spacing, and then also on the sheeting, hold down, slide down, stud, and the connectors. Anyway, with this transformation, we can, for each panel, define an equivalent panel. And so this is the model, and now we have implemented the solution intramuri. So you can see we have the equivalent panel realized by rigid elements. Then we define the diagonal in order to define the proper lateral stiffness and strength for these timber panels. It's important to underline that we had to introduce some offsets which are rigid elements hinged at their extremities in order to avoid introducing parasitic moment and forces into the model, and have only, let's say, shear that is going into the equivalent panels. So here we can see the results of the stiffened structure. So we can see right now that all the analyses are verified. I think the most important is to compare the pre and post retrofit intervention and compare the two curves. I must underline, this intervention does not affect the masonry. In fact, we see that the ultimate displacement capacity of the pre and post intervention is actually the same, because it's controlled by the failure of this element in here. What is affected is the shear capacity, which increases significantly, and well, the period of the equivalent structure. We can see that the curve of what we could call the hybrid structure is quite peculiar. So we have the first phase where we have loading the masonry, and then when we start cracking the masonry, we activate the timber panels. For this type of structure, it's non-trivial the definition of the equivalent period of vibration, because if we run a model analysis of the two models, we obtain exactly the same period. Here is 0.12 seconds. But due to the bilinearization, the equivalent bilinear curve has a significant difference. So we have 0.1 second in this case and 0.3 second in this case. Someone could argue that a possible bilinearization could be done reducing the intercept and catching the first elastic branch, so when the masonry remains elastic. We decided to go with the code-based bilinearization, mainly because it's more conservative and we obtain a larger displacement demand. In order to show that, well, I have prepared here 3 pictures. So this is the pre-retrofit. This is the post-retrofit with the 60% intercept bilinearization, and this is the post-retrofit with the 30% bilinearization. This vertical line represents the displacement demand for 3 methods, and 2 M&2 modified M2 and the capacity spectrum method. So what we see is that the structure pre-intervention is verified only with the M2 method. So this is another peculiar thing. With this method, we would verify the structure, while both the capacity spectrum method and M&2 method would predict failure. Here, instead, we see the 2 different bilinearization. As I said before, with the first bilinearization, we obtain a larger, higher acceleration capacity, but due to the larger period, we have also a larger displacement demand, so a lower value of alpha. In this case, instead, we obtained a lower with the second type of bilinearization. The important thing to underline is that with this type of intervention, increasing a lot the shear capacity of the resulting structure, we get really close to the elastic range. So the 3 methods, they predict basically the same displacement demand. And the last thing I would like to say, using the capacity spectrum method sometimes is tricky for seismic assessment, as I said before, because you can see in here that when we have acceleration capacity which are around the plateau for the maximum reduction, so this is maximum elasticity, you can obtain quite a big drop or increase in the displacement demand, which mean that a tiny difference in the acceleration capacity could induce big differences in displacement demand. This last slide is to conclude, to compare the pre and post intervention. So we can say that with the three methods, this slide just underlined what I said before. So that this retrofit intervention turned out to be effective for the strengthening of the structure, and still there are some question when using the three different methods, and particular attention should be paid in using the tree and choosing when to use the tree. With this, I conclude my presentation. Thank you all for the attention.
Thank you, Marco. Thank you again, all the speakers. We have no other questions from the audience. I think that this 3-hour session was quite interesting and various. We have provided say significant amount of say different presentation, different case studies, different application, but also similar application. I would say that something which was shown by Marco was also, I would say, compatible with what was presented also from in other presentation. For instance, in the presentation of Anastasis Tsiavos, had some similar solution that could have been modeled in a way that is say consistent with what presented by Mr. Tondelli. I think we can thank everybody, in particular all the participants that resisted till the end. I can ask you all to say hello, and I try to take a picture of all of us now. I will send you this picture with the final slide of the webinar. I thank you again, Professor Rita Bento, Professor Rocco Zarnic, Dr. Anna Simoes, Dr. Stylianos Kallioras, Mr. Georgios Papadopoulos, Mr. Marco Tondelli, Dr. Anastasios Tsiavos, Dr. Stylianos Kallioras, and 2 times, and Dr. Jacopo Scacco.
Thanks, Professor.
Thank you.
Thank you very much.
Thank you very much.
So I hope we can see you in person as soon as possible, and I also hope that many of you will be back with us in the 3rd Tremori event next year. Bye bye.
Bye bye.
Bye. Thank you.